I told you once in an earlier conversation about the barriers that make interstellar travel appear physically impossible using anything resembling conventional rocketry. The energy requirements that approach infinity as you near light speed, the exponential fuel penalties the rocket equation imposes, the dangers of interstellar dust at relativistic velocities. I stand by everything I said in that conversation, but I want to be fair to the physicists and engineers who haven't simply accepted that barrier as the final word and who have spent real, serious effort proposing approaches that might at least partially work around the worst of these problems. I want to walk you through the actual serious proposals, not the science fiction versions, but the ones that have appeared in real technical literature, been studied by real engineers, and in a few cases actually been tested in preliminary form. Let me start with the proposal that I find personally most connected to my own history because it emerged directly from the physics I spent years of my life working with, and because it was seriously studied by physicists I knew and respected. In the years after the war, a physicist named Ted Taylor, along with Freeman Dyson, developed a genuinely serious engineering proposal called Project Orion, studied through the late 1950s and into the 1960s, that proposed propelling a spacecraft not through conventional chemical combustion, but by detonating a sequence of small nuclear explosive devices behind the vehicle, with the resulting expanding plasma striking a large, heavily reinforced pusher plate at the rear of the spacecraft, transferring momentum through a shock-absorbing mechanism to accelerate the vehicle forward. I want to be direct about how strange this proposal sounds, and how strange it genuinely is, but I also want to be honest that the underlying physics is completely sound, and that this represents one of the very few propulsion concepts ever seriously studied that could, using technology understood even in the 1950s and 60s, plausibly reach a meaningful fraction of the speed of light. The physical logic behind Orion is straightforward once you understand it. Nuclear detonations release an enormous amount of energy in an extraordinarily short time, converting a small amount of mass into a correspondingly enormous release of kinetic energy in the resulting plasma, following exactly the mass-energy relationship I spent years calculating in far more troubling contexts. If you could direct even a fraction of that released energy into pushing a spacecraft forward, rather than dispersing uselessly in all directions the way a weapon detonation does, you would have access to a propulsion system with a specific impulse, the standard measure of propulsion efficiency, dramatically higher than any chemical rocket could ever achieve because you're tapping directly into nuclear rather than chemical energy release. Taylor and Dyson's engineering studies concluded that a sufficiently large Orion-type vessel detonating a sequence of nuclear devices at a carefully timed pace could theoretically reach velocities on the order of 10% of the speed of light, using extensions of the basic concept, potentially enabling the journey to a nearby star system within a human lifetime, something conventional chemical or even fusion propulsion struggles enormously to achieve. I want to be honest about why this proposal, despite its genuine theoretical soundness, was never pursued to actual construction, because the reasons matter for understanding the broader landscape of interstellar propulsion proposals. The most immediate obstacle was political and environmental rather than physical. The 1963 Partial Test Ban Treaty prohibited nuclear detonations in space, effectively outlawing the specific propulsion mechanism Orion depended on, a restriction put in place for entirely sensible reasons related to radioactive fallout and the broader dangers of normalizing nuclear detonations. Reasons I understood and largely supported, given everything I knew about the risks involved in nuclear weapons more broadly. Beyond the legal obstacle, there were serious unresolved engineering questions about the pusher plate's ability to survive repeated nuclear detonations without degrading, about the radiation exposure risk to any crew aboard the vessel, and about the practical difficulty of launching such a vehicle from Earth's surface without violating the same test ban restrictions during the initial ascent phase. Orion remains, to this day, a technically serious proposal that nobody has built, not because the physics fails, but because the practical and political obstacles surrounding nuclear detonation technology have proven so far insurmountable. The proposal that emerged as something of a successor to Orion's basic logic, while avoiding its most serious political obstacles, is nuclear pulse propulsion using fusion rather than fission, a concept studied extensively by the British Interplanetary Society through a project called Daedalus, conducted between 1973 and 1978, well after my own death. But building on physics, I understood the foundations of, throughout my career. Daedalus proposed a vessel powered not by external nuclear detonations against a pusher plate, but by igniting small pellets of fusion fuel, specifically a mixture of deuterium and helium-3, inside a magnetic confinement chamber at the rear of the spacecraft, using powerful electron beams to trigger inertial confinement fusion in each pellet in rapid succession, with the resulting fusion plasma channeled and directed by magnetic fields to produce thrust, rather than requiring the crude mechanical pusher plate Orion's design depended on. The Daedalus study concluded that a vessel using this fusion pulse propulsion concept could theoretically reach velocities of around 12% of the speed of light, sufficient to reach a nearby star system. In the study's specific case, Barnard's star, within roughly 50 years, using an entirely unmanned probe design rather than a crewed vessel. Given the enormous scale and complexity the propulsion system would require, I want to emphasize how serious this study actually was, because it's sometimes mischaracterized in popular discussions as pure speculation. The engineers involved worked through detailed mass budgets, fuel requirements, and structural considerations with the same rigor I associate with serious aerospace engineering studies, concluding that while the concept remained far beyond any technology that existed in the 1970s and remains considerably beyond current technology even now, it didn't require any fundamentally new physics, only substantial advances in fusion ignition technology, magnetic confinement engineering, and the ability to mine helium-3, a fuel isotope that's exceedingly rare on Earth, but believed to exist in more workable quantities on the lunar surface or within the atmospheres of gas giant planets, adding yet another layer of infrastructure the mission would require before it could even begin. I want to turn now to a fundamentally different category of proposal, one that abandons the idea of carrying propellant aboard the spacecraft entirely, sidestepping the exponential fuel penalty of the rocket equation in a genuinely clever way. This approach is generally called a light sail or laser sail concept, and its most seriously funded modern iteration is a real, ongoing research initiative called Breakthrough Starshot, announced in 2016 with backing from physicist Stephen Hawking, among others, and continuing active technical development in the years since. The basic physical principle is, one, I find genuinely elegant. Light itself carries momentum, even though photons have no mass, a direct consequence of relativistic physics, where momentum depends on energy and velocity. rather than mass alone for massless particles. When light reflects off a surface, it transfers a small amount of that momentum to the reflecting object, producing a tiny but real force called radiation pressure. This force is far too weak to be useful for ordinary propulsion using sunlight alone, but if you concentrate an enormously powerful, tightly focused laser beam onto an extremely lightweight, highly reflective sail, the resulting force, sustained over a long enough acceleration period, can theoretically accelerate a sufficiently small spacecraft to a substantial fraction of the speed of light. Without that spacecraft needing to carry any propellant of its own at all, the propulsion energy source, the laser array, remains behind either in Earth orbit or at some other fixed location, rather than needing to be carried aboard the accelerating vessel. Breakthrough Starshot's specific proposal involves a ground-based or space-based array of powerful lasers focused with extraordinary precision onto a sail measuring only a few meters across, but weighing only a few grams, attached to a spacecraft, sometimes called a starship, weighing only about a gram itself, carrying miniaturized cameras, communication equipment, and scientific instruments at a scale that would have seemed like pure fantasy to engineers of my own era. But that has become genuinely plausible, given the extraordinary miniaturization of electronics achieved over the past several decades. The proposal's calculations suggest that a laser array, delivering on the order of 100 gigawatts of power, focused on the sail for a period of just a few minutes, could theoretically accelerate this tiny spacecraft to roughly 20% of the speed of light, enabling a flyby mission to Alpha Centauri, the nearest star system, within approximately 20 years of launch, plus the additional 4 years required for any data or images the spacecraft captures to be transmitted back to Earth at the speed of light. I want to be honest about the genuinely serious engineering obstacles this proposal still faces, because I think honest assessment matters more than either uncritical enthusiasm or dismissive pessimism. Building a laser array capable of delivering 100 gigawatts of focus power, comparable to the output of dozens of large power plants, concentrated into a single, extraordinarily precise beam, represents an engineering challenge well beyond anything currently constructed, requiring advances in laser technology, power generation, and beam focusing precision that remain active areas of research rather than solved problems. The sail material itself needs to be extraordinarily thin and lightweight while surviving the tremendous heat generated by absorbing a fraction of that enormous laser power during the brief acceleration period, a materials science challenge that researchers are actively working on but haven't yet fully solved. And even if the technology is perfected, a spacecraft this small and lightweight, traveling at 20% of light speed, faces exactly the interstellar dust collision risk I described in our earlier conversation, requiring the tiny craft to survive impacts from interstellar particles at extraordinarily high relative velocity, a risk the mission's proponents acknowledge remains only partially addressed by current shielding proposals. There is a further category of concept I want to address, one that abandons entirely the goal of reaching another star within a single human generation, and instead embraces multi-generational timescales directly, the concept generally called a generation ship, or in a more technically refined version, a world ship. This idea proposes not solving the propulsion problem to achieve extraordinary speeds, but instead accepting a much slower journey potentially spanning hundreds or even thousands of years, aboard a vessel large enough to function as a genuinely self-sustaining, closed ecological and social system with the original crew's descendants, rather than the original travelers themselves, eventually arriving at the destination star system generations later. I find this concept fascinating, less for its propulsion requirements, which are actually considerably more modest than the other approaches I've described, since a multi-century journey doesn't require anywhere near the extreme velocities the other proposals aim for, and more for the extraordinary engineering and sociological challenges it raises instead. A genuine generation ship would need to solve problems in closed-loop life support far beyond anything even the International Space Station systems, which still depend on periodic resupply from Earth, have ever needed to achieve, recycling air, water, and nutrients with near-perfect efficiency over a timescale of centuries, while somehow maintaining a stable, genetically diverse population large enough to avoid the serious problems of inbreeding depression across many generations, confined to a single vessel, all while preserving the technical knowledge, social cohesion, and motivation required to actually complete the mission across a span of time longer than most nations in human history have managed to maintain political continuity. I want to draw your attention to a specific engineering study that took this concept seriously, called Project Orion, a design competition organized in 2011 through Icarus Interstellar, a nonprofit organization focused on interstellar research, which invited serious engineering teams to work through the detailed requirements of a genuine multi-generational world-ship design, including population dynamics modeling, closed-loop ecological system requirements, and radiation shielding sufficient to protect a population across centuries of continuous interstellar transit. The study concluded that while no fundamental law of physics forbids a world-ship concept, the engineering and social challenges involved were, in some respects, even more daunting than the propulsion challenges facing faster interstellar travel concepts, because a world-ship failure mode isn't simply a mechanical malfunction. It could involve the gradual social or biological collapse of an entire self-contained human society, unfolding over a timescale too long for any single generation of crew members to fully diagnose and correct problems that might only become apparent decades or centuries into the voyage. I want to mention one further avenue of research that I find genuinely exciting, precisely because it approaches the interstellar travel problem from an entirely different direction than any of the propulsion concepts I've described so far. Research into whether general relativity itself might permit shortcuts through space-time that wouldn't require reaching anything close to light speed at all. I discussed the Alcubierre warp drive concept in our earlier conversation, and I want to add to that discussion by mentioning a related and in some ways more theoretically grounded concept. Traversable wormholes, first studied rigorously by physicist Kip Thorne and Mike Morris in 1988, working through the mathematics of whether general relativity's equations permit a stable, navigable shortcut connecting two distant points in space-time, potentially allowing effective travel between star systems without the traveling object ever needing to move at anything approaching the speed of light relative to its immediate surroundings. Thorne and Morris's mathematical analysis concluded that traversable wormholes are not forbidden by general relativity's equations, but that maintaining one in a stable navigable state requires, just as the Alcubierre drive does, exotic matter with negative energy density in quantities and configurations that remain entirely beyond anything physics currently understands how to produce or control. I find myself in a position with wormhole physics, similar to where I stand with the Alcubierre concept, genuinely fascinated by the mathematical rigor and legitimacy of the theoretical work, while remaining honest that the practical requirement for exotic matter represents an obstacle that current physics offers no clear pathway around. rather than merely an engineering challenge awaiting sufficiently advanced technology. I want to close by trying to synthesize what I think the honest state of this field actually is, because I think it's more nuanced than either the pure pessimism of my earlier conversation or an uncritical enthusiasm for these proposals would suggest. Every serious concept I've described in this conversation, nuclear pulse propulsion, fusion pulse propulsion, laser-driven light sails, generation ships, represents genuinely rigorous engineering thinking, worked through by serious physicists and engineers, using physics we understand and largely trust. None of them requires new, undiscovered physics the way faster than light travel does. And yet every single one of them remains, even now, decades after the earliest of these proposals were first seriously studied, firmly in the realm of theoretical design study rather than actual engineering practice, separated from construction not by any law of physics, but by engineering challenges, resource requirements, and in some cases political obstacles that remain, honestly, comparable in scale to the challenges I spent years of my own career helping to solve at Los Alamos. I think the most honest thing I can tell you is this. Interstellar travel, using velocities well below the speed of light, Orion's 10%, Daedalus is 12%, Starshot's proposed 20% for a tiny unmanned probe, does not violate any known law of physics, and represents an engineering challenge that, unlike faster-than-light travel, is at least theoretically achievable using extensions of technology and physical principles we already understand and have partially demonstrated in laboratory or small-scale settings. What separates these proposals from actual functioning interstellar spacecraft isn't a missing piece of fundamental physics. It's the same kind of enormous, multifaceted engineering and resource mobilization challenge that took the United States years and an entire dedicated national laboratory to solve for a considerably smaller, though no less consequential, technical problem during my own working life, whether humanity ever actually commits the resources, the sustained institutional will, and the multi-decade or multi-generational patience these proposals would require remains, I think, a question of choice and priority, rather than a question the laws of physics have already answered for us.